One of the features of the FWD/HWD back calculation module is the FWD utilities section. In this part of the apps, you can, for example, load FWD Time Load history. By doing that, to do that, we have to switch to the FWD Time History tab, then select Open File. Just like before, we have to make sure that the method that we select here is compatible with the source of the data that we are trying to open. And at the moment, the app is compatible with the following sources or origins. We have GILS, Pave Testing, Rinsant, and Dynatest. In this case, this is a GILS file, so I'm going to select the GILS method here and open it. When I open it, I can view a heat map of the normalized deflections, the same as we saw in the first in the FWD main window. The difference is that in this part of the apps, I can switch this representation in between the absolute magnitude as it is now, so absolute values, and I can visualize the same information in percentile. You see that this is exactly the same information, but now the scale goes from 0 to 100 because it's in percentile, so the, the, the limits are 0 and 100, while if we switch to absolute values, the limits are the minimum and maximum deflections that were collected during the FWD test. I can also visualize the same exact information, but in terms of the shear wave speed, so I can see it in absolute values and percentile, and the same for the deflection lag load. If we select any particular drop of any particular FWD station, the apps will allow us to play a slow motion movie of the test. So this symbol here represents the load, and this line here represents the surface of the pavement as measured with the FWD sensor. Of course, that in an FWD test, we only have sensors in one direction, but if we mirror that deflection to the other side of the equipment, we can obtain a full deflection bowl, although only 50% of it is actually measured. We can also obtain the parameters for each drop, such as shear speed and lag. If we click on the line, if we select a line that corresponds to a station instead of a drop, we are going to be able to visualize the deflection bowls of all the different drops and see how they compare to each other. Another thing that we can do with the time load history files is to save them to the HTOF format, to a generic HTOF format that will convert all of this information. So I'm going to play the slow motion movie. So an FWD test lasts for approximately 30 milliseconds. During those 30 milliseconds, as much as 1,000 measures are recorded. So we are going to have. So let's say that we have one. We always need to know the peak load, and we always need to know the maximum deflections that were recorded for each sensor, because those are the values that are actually used in static FWD back analysis. But those, imagine if we have an FWD machine with 9 sensors. So that's the same thing as to say that we only need um, that we only need um, 10 values, so the load and one maximum deflection per each sensor. But the truth is that if we measure the load and the deflections in each sensor with an interval of 0.1 milliseconds during 30 milliseconds, we are going to get um, hundreds, if not more than 1,000 values. Although we only need, for practical FWD back calculation purposes, we only need a fraction of that number, and that it's the conversion between um, time load history data and the usual FWD raw data that this option of saving to the ASHTO format enables. Uh, the FWD utilities window also has another very interesting feature, which is the possibility of conciliating GPR data and FWD data. So let's imagine that we have an FWD uh, raw data file. So something very simple, like we've seen before. We can also visualize it in terms of absolute values or in terms of percentile, and that we also have for the exact same stretch of pavement that was tested with the FWD machine, that we have GPR tests as well. And GPR data looks something like this. So this is a text file with this is a text file that has GPR data associated with it. So the first column will be distance. The second column will be the depth from the surface at which the bottom layer of the first layer is refracted, and the third column will correspond to the depth at which the bottom face of the second layer is refracted. And if we open this information in depth, this is what we are going to see. So these points are the points that are depicted in that raw data file that we just saw. And if we connect these dots, instead of having just isolated points, if we connect these dots, we will have the contour of the layer. So this will be the contour of the surface layer, and this will be the contour of the intermediate layer. In this case, there are only two. So as you can see, the thicknesses of the layers vary a lot. So if we want to use this information to automatically create pavement construction data, what we have to do is, in this case, that I know I have only, in this case we only have two layers. So once again, I'm going to select two layers. You know that the first layer is asphalt concrete. The second layer is a granular base. I'm just going to introduce random seed moduli as we've done before. Now I'm going to introduce the thicknesses, although these thicknesses will not be used. The only goal is to complete the information. And then I'm going to select this option here that says apply thickness correction, so that we can use the information of the GPR data. And then I'm going to save the structure, and I'm going to call it GPR layer thickness. Save it. Then I'm going to open that same file in the main FWD window, the national file. Now I'm going to load the pavement construction data that I just created using the GPR data. And as you can see, we have a pavement construction data that consists of 8 sections. So right now we are visualizing section number 1 out of 8. And if I keep moving forward, you'll see that we have 8 sections. And why 8? because the maximum number of FWD stations that this raw data file that I'm using as an example is 8. So we only have 8 stations. So when depth associated the GPR data that was collected with the GPR test to the FWD data, what it did is search for the GPR test that was closer in terms of distance to each particular FWD station, and then automatically use that pavement information and layer thicknesses to automatically define the pavement um, structure that is closely related to this particular distance. This means that when we are using and when we are conciliating GPR data with FWD data, we have to make sure that the point in which the FWD tests consider a distance of 0 has to be exactly the same point that the GPR test consider as 0, because the correlation between the pavement sections, the different layer thicknesses, and their corresponding pavement sections, and the FWD station is made using the distances that are stated in both the FWD raw data files and in the GPR test data information.